All right. My name is Manu. This is Malte. Our names sound funny in any language. That's just how it is. We just graduated from NTNU in Trondheim and just started working in Knowit. And that pretty much sums up the relevant parts of our lives. We wrote our master's thesis about something involving deep learning. So today we thought we'd give you an introduction to deep learning. This is the agenda. We're going to start out talking a little bit about the relationship between artificial intelligence, machine learning, and deep learning, because those are the terms that you hear a lot about these days, but you might not know what the difference is and stuff like that. Then we're going to move on to talking about machine learning very briefly, because you need to know what that's about to understand deep learning. At this point, Malte is going to introduce or talk about how neural networks work, because that's what deep learning is about, deep neural networks, basically, in a nutshell. Towards the end, we're going to show you some cool stuff from the deep learning world, what we've gotten lately from this. And in the end, we're going to mention a few frameworks which you can use to build your own models. So artificial intelligence is the term that describes the entire area, the entire field. And machine learning is a subfield of artificial intelligence. So AI development is about creating machines that can exhibit intelligent behavior, which often transfers to human behavior as we use it. And so there are other aspects of artificial intelligence that doesn't actually involve machine learning. And similarly, you have deep learning, which is a subfield of machine learning. And we're going to get more into this later. So who's this guy? This is Garry Kasparov, a grandmaster of chess. You've probably seen some of these images before or heard about it before. In 1997, he was beat by a computer, Deep Blue, which was quite impressive then. It's still an impressive feat. And why I'm mentioning this is because Deep Blue isn't really machine learning. They didn't use machine learning to create Deep Blue. It exemplifies something called symbolic AI, good old-fashioned AI. And I'm not going to get a lot more into that, other than saying that they built Deep Blue by optimizing search and evaluation functions to find the best moves in chess, right? And the thing is that throughout the course of AI development, computers have always been able to easily accomplish a lot of things that are mentally challenging for humans, right? Beating Garry Kasparov in chess isn't really easy for any of us, most likely, but a computer was able to do it. The thing is that the most difficult things for computers have always been doing what's easy for us, right? Understanding speech, identifying objects, knowing that if you see a dog, you know that it's a dog, right? So the thing is that though chess is a fairly complex game, it is quite easy to describe chess formally, right? With rules programmatically, because there's a set board size and specific pieces that can move in a specific way. But how are you supposed to do that with, like, how are you supposed to describe what a dog looks like, right, to a computer? And early approaches in AI tried to kind of hard code knowledge like this about the world, but it didn't really work out. And that's how machine learning came into the picture, right? So, in a nutshell, machine learning is about a computer learning from experience. We don't actually program what it's supposed to do. It's supposed to learn this by itself. And it does this typically by us giving it a data set of training samples. And using a learning algorithm, it'll approximate a mathematical function that solves the problem. The goal is to generalize to new instances of the problem based on this training set. I'm going to take a sip of my coffee and you're going to have time to look at this. The thing about machine learning is that it's often hard to interpret results. So if something doesn't work the way you want it to, it might be difficult to know what to do next, right? But it's not impossible. If you have a little bit of in-depth knowledge about what's going on underneath, you might be able to interpret results and build on this, right? But it's not like other algorithms, because often you don't really know how to solve the problem. You're just letting the machine figure it out by itself, and it's finding patterns that you're not able to see explicitly. Broadly speaking, you can divide machine learning into 3 separate categories. You got supervised learning, unsupervised learning, and reinforcement learning. Now, we're kind of tight on time, so I'm only going to talk a little bit about supervised learning, because this is the field where we've been able to accomplish the most in recent years. Essentially, you have a data set with training samples from the area, like the problem area, containing specific features. So if you want to create a system that is able to take in an image and tell you if this is, or if you want to build a system that can take in an image of a car and tell you if it's a BMW or an Audi, right? The make or the brand. You might feed it a data set of a lot of images so that it can find patterns, and you'll also give it labels which contain the correct answer, right, to each image, if it's a BMW, Audi, and all that stuff. And based on this, it will learn. And this is called classification. And by the way, if there are any questions throughout the presentation, I was going to say that please don't ask them because we're tight on time, but I mean, if something's unclear, just go for it and we'll figure it out, right? So deep learning is, as I said, a subfield of machine learning. Essentially, it's about deep artificial neural networks. It's called deep learning because typically the neural networks, they contain layers, right? And in deep learning, you have a lot of layers, many layers. Initially, neural networks were inspired by how neurons in the human brain function, and that's why it's got its name. But I wouldn't say that deep learning is trying to simulate human brain function as it is today. Now, you might wonder if there is something called shallow learning, or maybe you don't, but anyway, there is something called shallow learners, and basically those are the traditional machine learning algorithms, right? Support vector machines, logistic regression, decision trees. Some of you have probably worked with these before. So what's the difference? The difference is that when you work with machine learning, you often have to pre-process your data, figure out what features of your data are important for the classification, right? And that's something you really got to do when you use algorithms like these. But with deep learning, theoretically speaking, you might be able to, or you often can just feed it raw data without processing them too much before you feed them into the network. Like if you're working with text, with a traditional algorithm, you might have to figure out which types of words are important for the classification and filter them out before continuing. But with deep learning, you might be able to just put everything in there, and you'll just rely on the algorithm to figure out what's important by itself. Another thing is scaling. Research shows that with deep learning, you can continue to improve the performance by adding more training data, right? With other algorithms, like the ones mentioned, you might hit a point where your prediction accuracy does not improve. And now Malte is going to talk a little bit about neural networks.
I'm holding it.
Yep.
Yes. Okay. You know, I like soccer. I'm a soccer player. So I thought I was gonna start with an example to showcase how a neural network works. By the way, the goal of this is just to get you guys to understand like the underlying mechanisms, not the math behind it. There's going to be a bit of math, but it's not that important because all your frameworks are going to do them for you. So let's say you want to measure a soccer player's performance. And the only feature you look at is his ball control. So as the ball control increases, the performance increases as well. In a neural network setting, this would be written like this, where the neuron, the circle here, the ball control is fed into the neuron. The neuron does some kind of math formula stuff on it. And then it spits out how good the player performed. This function is called the activation function of the neuron. And in this case, the activation function would just be this. But if you want to look at more features of a player, you can look at how fast he is at sprinting, his stamina, his ball control, and how well he can shoot at goals. And you can kind of abstract these into other layers. So for instance, you can abstract sprint and stamina into a neuron, which maybe says something about his mobility or his movements over the field. You could, for instance, add up sprinting and ball control and say how well he could beat an opponent. Or you could add shooting and ball control together to get how well he's at scoring goals. And then these are then fed further into another neuron, which then gives us the performance of the player. So here we have a small neural network. We have 3 layers. This is the input layer. Then we have the hidden layer, which is kind of able to understand abstractions of what you're putting in. And then this is the output layer. Now the size of the input layer, there's only one input layer. The size of this is dependent on what you're trying to solve, what you're looking at. In our case, it's 4, since we're looking at 4 features, but in a picture, it could be 1 million, for instance. And then the hidden size kind of depends on the complexity of your problem, but it could be 1 or it could be 1 million too, not as constrained by as the input layer. And the output layer, the same as the input layer, it depends on your problem. In our case, we just want one number from the system. So we have 1 neuron in the output layer. Now something you usually do is that you fully connect all these layers to each other. And this is so that the network itself can learn what is important. When you feed in these values and you want a particular value out, the system can then learn itself which ones it wants to focus on which neurons. Let's talk about the neuron for a little bit to see how it calculates stuff. So this is the neuron, this is the activation function, and then it takes any amount of input in. In this case, it's 3. And then it outputs 1 value. I want to introduce 2 more features of it. The first is the bias. It's kind of a threshold for the activation of the neuron. And then for each connection here, we also introduce weights. So that when you now calculate what should be the input for the neuron, you now add all of this up and run it through the activation function, and then it runs out. Just a quick example. This is the mathematical formulas. Not that important. Don't worry about that. We're just gonna do really fast. So you take the input x1 times the weight of this connection, which is 1. So it's 3 times 1 plus 2 times 1 plus 2 times 4 plus 2. This is the input of the neuron, which is 15. And then this activation function, I just made one just for simplicity. It just feeds out whatever you give it. So the output of this neuron is 15. Just want to mention that activation functions depends on what you want your neural network to do. And there could be a lot of different ones. I just chose an easy one for illustrating it.
Malte, I think there's a question here.
Oh, yeah.
When you're doing supervised learning, do you do a lot of manual tweaking of the weights?
Good question. We're going to come to that. So the first thing when you are going to train a neural network is that you kind of need a data set. And we're just going to use Manu's example here of supervised learning, where we have a data set. In the soccer example, it would be a data set of a lot of soccer players having numbers for their stamina and shooting and stuff. And then you have the performance of the player as well. So you know the input and you want to learn a specific output. Now, the weights of these connections are then initialized. Okay, then you have to first make the architecture of the network. It can be whatever. Here we just have an input layer, which is the size of the features. Then we have 2 hidden layers with size 3 in this layer and 4 in this layer, just because you can. And then we have 1 output, because we need one value out of it. And then we initialize the weights randomly. So all of these weights are just completely random. And then when you train the network, everything depends on finding the optimal weights. So it learns the input and the output. This is done in 3 parts. The first part is called the forward pass, where we just take our values. So let's say the soccer player has, he's 7 in stamina or something like that, and 5 in shooting. And then you pass it through, you calculate all the math stuff, and then you get an output. And let's say he's 3 in performance, and then you measure how wrong that is, because we also know what his real performance was. Yeah. And then we can, the next step is to calculate how wrong we are using more math. And by that, we can then go backwards, layer by layer, and we can slightly alter the weights so that it gets a little more correct. And then we do it again many times. I just want to mention quickly that just like activation functions in the neurons, there are a lot, the error function, there's a lot of different error functions that are used depending on what problem you're trying to solve. And then the backward pass is called the backpropagation algorithm, which I'm not going to talk about today because it's kind of out of the scope of this presentation. Yeah. So let's just take a quick example. Let's say we have this architecture of a neural network. This is the input layer, 2 neurons here. This is the hidden layer, 2 neurons here, and 2 neurons in the output layer. And then the biases for each of the layers. Yeah.
What does the bias do, and how do you set it?
The bias is kind of a threshold for your neurons. It kind of says when they're about to activate. It's kind of difficult to explain really fast.
Basically, like, can I answer? Or?
Yeah, sure.
So each neuron is kind of.
Can you please pass
Oh.
the mic
Oh,
and
yeah.
also please repeat your question?
I can just talk into it, right?
Yeah.
Like.
Please also repeat your question.
All right. So the question was, what does the bias do, right? So basically, each neuron is kind of detecting features, like he was talking about, like hidden layers detect features like mobility, maybe, right? Because we don't really know. It's just hypothetical. And when they detect a feature, they kind of activate or they fire in deep learning terminology. So the bias sort of says how easy it is for a neuron to fire. And that's why it's called a bias, right?
It's like a threshold value.
Yeah, kind of. Do you want to add something?
Yeah, I want to add something. It's the real use of the bias is when you have inputs that can be zero, and that.
Should he talk into that? Yeah, let him talk.
Maybe it may be very technical, but for instance, if you have a network which is to find out does water freeze at this temperature, or is this the freezing point of water, then getting a 0 in and multiplying that by weight, and you want a 1 out, then you would have to have a bias to like add 270 Kelvin or something to get to that point. So the bias is to provide some input for that. Yeah.
Yes, exactly. It could be like, often it's like constants like the freezing point of water or in Kelvin, or it could be like the speed of light or something. Yeah, okay. All right, let's just do a quick example of this. We're not that bad on time. Let's say that we initialize the weights to be these values, just randomly chosen, kind of. And then we want the network to learn that given these two values in the input layer, 0.05 and 0.1, we want the network to learn that on this neuron, it should output 0.01 and this one 0.99. You can think of it as that this is maybe the height of a person and this is the weight. And then we want to figure out if he is a featherweight boxer or if he's a sumo wrestler. So in this case, given these, it's kind of probable that he's a sumo wrestler. So we just do it like we did with the neuron. We just start with this one. We calculate what the value in is. It's I1 times weight 1 plus I2 times weight 2. And then we add the bias. And then we get this number. And then this is called this is the activation function. It's called the sigmoid function. And it just, I just want to showcase that you can use different ones. All depends on what you want to do with your neural network. And then the output of this neuron is going to be this number here. And then we can do the same with H2. We get this number, and then O1 and O2, and these get these numbers. So we see that the neural network now outputs 0.75 on this one. And we want it to output 0.01, so it's pretty bad. And then it wants to, we output 0.77 here, but we want to have 0.99. It's better, but it's not good enough. So this was the forward pass, was the first step. Then we want to do the next step. We want to calculate how wrong it is. And for this, we can use the squared error function. And depending on your application or your problem, you use other error functions. This is the mathematical formula. You basically just take the error of this plus the error of this. You take the target minus the output squared. So in our example, it would be this value minus what we got, 0.75. And we get that it's 0.27 wrong. It doesn't really tell us anything yet. And then the same with this one. We want 0.99. We got 0.77, and then we get this wrong. And then we add them together, and we get 0.298. So that's how wrong our neural network is right now. Then we know how wrong it is. We can do a backward pass. The goal of this, I just want to mention, is that we want to figure out how much each weight affects the total error. So you kind of, I'll do some partial derivation stuff. I'm going to do it here. Anyways, when you do the backward pass, you change the weight slightly. And then we plug in the same numbers here, or different numbers, depending on your data set. And then you do the forward pass again, and then you calculate how wrong you are. So the first error we got was 0.298. And if we go do the backpropagation once and then do the forward pass and calculate how wrong we are again, then our new error is going to be 0.29. And then you do this 10,000 times, and the error is going to be really small. This neuron is going to output 0.016, and this neuron is going to output 0.98, which we're now a lot closer than when we initially started by randomly setting our weights. The math is not that important, and if anything was unclear, then just know that there are layers, there are weights in the connections, and we update these weights depending on our training data and what we want to do with it. Yeah, I think that's it. Yeah.
Question.
Yes, first of all, I'm totally new to this subject. And,
Yes.
probably you come back to that, but as I see you manipulate or to figure out how you can calibrate the weights by 3 steps, something like that, based on the targets. And I mean, the targets is something human or you know how to solve the problem. But when you try to manipulate the weights and all the parameters in the neural networks, how intelligent will this be? I think then it will react and give you the solution exactly what you want to, not what you expect to have.
Yeah, that's the thing. Even if you have the data set to something, it doesn't really mean that you know the solution yourself. But it is going to try to mimic whatever you put in. But the idea is then that whatever you put in is going to be represented well by the next thing that's going to come, and then it can kind of learn from previous experience. It can kind of predict, if you give it new numbers, what's going to be the output. Another thing you do, especially in deep reinforcement learning, is that you kind of make up a data set on the go. That's how you learn self-driving cars to drive, for instance. You did add anything at?
Another thing is what is different between this and the supervised learning, because you provide the answer, the labels to.
But this is supervised learning.
Yeah, this is supervised. Yeah, this is supervised learning.
Okay.
Yes, it is supervised learning. It's just figured out to perform better than other algorithms.
Okay.
Yeah,
So,
in a very short version. Yeah. Yeah. Okay. I hope that answered your question.
Yeah.
Yeah.
You want to give me the thing?
It would be great if you repeat the question.
Yeah. We will do that next time.
Next time.
But yeah, basically this was an example of supervised learning. You do have something called unsupervised learning, which would entail that you don't have those labels, right? Because those labels are based on like human knowledge, right? So basically we're just training the network to act like we would. But with unsupervised learning, you're only feeding it the features of the dataset and not the labels. And you're depending on implicit patterns to be discovered, right? All right. So what he just explained is called a feed-forward neural network. There are other kinds of neural networks too. This is called feed-forward because all the arrows you saw in the graph, they were going forwards, right? Data is being fed forward. You also have other kinds of network where you feed the data back to itself in the neuron. We're not going to get into that. My point is that the concepts and algorithms that are being used today have existed for a long time, right? So that's why you might wonder, why is this big now, right? Like for the last 10 years or so, deep learning has been getting bigger and bigger. There's a lot of talk about it right now. So one reason for this is that we have access to more data. And we have access to a lot of large labeled data sets. And as I said earlier, deep learning systems get better when they get a lot of training data, right? Also, we have access to larger amount of computational resources, meaning faster CPUs But maybe more importantly, we've started to use general purpose GPUs. GPUs were earlier used mostly for gaming, video games, but now we've been reusing it to train deep learning systems. In the training of neural networks, there's a lot of parallel operations, and with GPUs, you can do that more efficiently. So it's a lot faster than using a CPU. Impact on the real world. What I mean by that is that for every new success story within the area of deep learning, the time it takes until the next one is going to be shorter, right? Because more people are going to get into this stuff and start working with it, and it accelerates. Now we want to show you some stuff that's been happening lately within this field. Is the slide like skewed or something? Like,
No, it's good.
all right. So this is an old Chinese board game called Go. Some of you have probably seen this before. Last year, Google made a system that learned to play Go. And since then, it has beaten the best players in the world in Go. The system is called AlphaGo. It's a deep learning system. And this is really impressive because in Go, you got 10 to the 172 valid states. That's a big number. In chess, you got 10 to the 50. And chess is still really complex, right? That means that you can't create a system that brute forces Go. That's not feasible. What's also really cool is that during one of the games, the program made a move that stunned the experts. They didn't really understand it. They were confused. But later, it's been recognized as an ingenious move. And apparently it learned this move by training against itself. And it shows that we can actually learn from machines too, right? Deep learning has been used to identify cancer cells. They did this at Harvard. The system was able to correctly predict 92% of the introduced images. The doctors did a little bit better. But the fascinating thing is that together they covered almost everything. And it shows why it's usable. So deep learning has been doing a lot of good things in computer vision. We've been able to produce a lot of usable results, or not we, but other people. In the past few years, Google's been able to produce a really good image recognition system. Essentially, you can feed it an image of a variety of things, and it's gonna tell you what kinds of objects there are in the image. So if you give it a picture of a dog, it'll tell you there's a 99% likelihood of there being a dog in the image, right? They've been also experimenting with stuff. So they did that with this system by reversing the functionality, kind of. So when you feed an image to this Google Deep Dream, it's called, it will enhance the features that it detects of objects that are not necessarily in the image. It will enhance them so that it might seem like those objects are in there anyway. It's easier to show this, right? So this is an image of the city hall, and you feed it to the system and you get this out, right? Basically, you see a lot of shapes of stuff that's not there, It looks kind of funky. It's like a monkey there or something. This is Joachim. You might know him. We told the system that this is a picture of a dog, right? So it tries to detect features of dogs, and it enhances them. And then you get this. This is Malte in California. And suddenly he looks more like a bird or something, right? There's a monkey there or something. There's always a monkey. All right, we're going to conclude the presentation now by mentioning a few frameworks for using with deep learning. So Torch is a framework by Facebook, I believe. We haven't really used it. But we both used TensorFlow and Keras before. And Keras is basically a high-level framework, abstracting a lot of the functionality in TensorFlow. It uses TensorFlow in the backend. You can also use something called Theano, but TensorFlow is more popular now, I think. So it's a lot easier to use Keras because you don't have to get into the intricate details that you might have to get into if you use TensorFlow. You know, you can avoid all that math stuff he was talking about earlier, right? So we had to leave out like a lot of details in this presentation because the area is so big. You can't fit everything into a 30-minute long presentation, but hopefully you guys learned something, right? All right. Right.
Right?
Yeah. Right. Right.